In this video, we will begin discussing how to handle an E2 mechanism that occurs on a ring rather than on a straight chain molecule. In a previous video in this series, we saw that there is free rotation allowed around a single bond in a straight chain, while there's no rotation around a double bond. Now here we've specified free rotation around a single bond in a straight chain. So how would this apply to a ring? Rings impose rigidity. There's no free rotation around a single bond in a ring. No free rotation around a single bond in a ring. Well, here's the application of this idea. In this picture, we would say that the bromine and the methyl group are trans to each other because they're on opposite sides of the ring. The bromine is in front of the ring and the methyl is behind the ring. In this picture, we would say that the bromine and the methyl are cis to each other. The bromine is in front of the ring, and the methyl is also in front of the ring. Now, is it possible to take this trans picture and rotate around the single bonds so that the groups are cis? Can we rotate around this single bond so that these groups are cis to each other? No. There's no free rotation around a single bond in a ring. There's no way to rotate around this bond to get the methyl group to be on the same side of the ring as the bromine. Therefore, our molecule A and molecule B, are these two pictures of the same molecule, or are they two different molecules? Because there's no way to rotate this picture to make it look like this picture, molecules A and B are considered two different molecules. To be more specific, we would say they're stereoisomers of each other because they have the same connectivity but a different arrangement of the substituents in space. A ring where the substituents are trans is considered a different molecule from a ring where the substituents are cis because there's no way to rotate around the single bond to change this picture into this picture. Rings impose rigidity. So there is free rotation around single bonds, but only in a straight chain. There's no free rotation around a single bond in a ring. Now this is a little complicated because there is a limited amount of bending and folding that is possible around single bonds in a ring. A ring is not completely rigid. A ring imposes rigidity, but it's not completely rigid. You should already have learned that you can take this ring and fold it into chair cyclohexane. And then you could fold it in, you could do a chair flip and do a different conformation of chair cyclohexane. So there definitely are ways to bend and fold around the single bonds in a ring. There's no free rotation, but there is a limited amount of bending and folding possible in a ring, which allows you to make chair cyclohexane and then do a chair flip into the other conformation of chair cyclohexane. You could also fold this into the boat conformation that you might have seen earlier in your class. So there's limited bending and folding possible in a ring, but no free rotation. Well, none of that limited bending and folding would allow us to change a trans arrangement into a cis arrangement. So these really are considered two different molecules from each other. In the previous videos, we learned these ideas and applied them to straight chain molecules. We learned that the major product for E2 uses the more substituted beta carbon. Now remember, that's just the major product. You can also get a minor product using the less substituted beta carbon. We saw there's an exception. The major product for E2 with tert-butyl oxide uses the less substituted beta carbon. And we learned a requirement for E2. E2 requires the leaving group and beta hydrogen to be anti-periplanar from each other. Now, both of these ideas still apply when E2 occurs on a ring. These ideas still apply when E2 occurs on a ring, but the manner in which we apply these ideas will be different on a ring. So here's an extension of our E2 guidelines, where we've included a new column dealing with how to draw an E2 mechanism on a ring. So our first guideline here is that the beta hydrogen for E2 on a ring must be trans to the leaving group. This is a requirement, and it's a consequence of this idea. We know the leaving group and the beta hydrogen must be anti to each other, pointing in opposite directions. Well, the only way that the beta hydrogen and the leaving group can point in opposite directions when they're on a ring is when they're on opposite sides of the ring. If the beta hydrogen and the leaving group were on the same side of the ring, cis, there's no way that they could be pointing in opposite directions. No way that they could be anti. So for E2 on a ring, you can only use a beta hydrogen that's trans to the leaving group. Now, our next guideline is clearly an extension of the Zaitsev and Hofmann rules. On a ring, the major product for E2 will continue to use the more substituted beta carbon. But, of course, only if that beta carbon has a hydrogen that's trans to the leaving group, as we saw in the previous guideline. There's still an exception. When you use tert-butyl oxide, the major E2 product on the ring will use the less substituted beta carbon, but only if that less substituted beta carbon has a hydrogen that is trans to the leaving group. So this guideline is an application of this idea, combined, I suppose, with this idea as it applies to a ring. Please pause the video and try this problem. Now let's discuss. We can start by numbering the carbons, including this one. I won't bother numbering this carbon because this turns out to be an unreactive solvent in this reaction. So now we can identify some roles. The O- we expect to be a nucleophile or a base. Neutral chlorine looks like a leaving group. So carbon 2 will be our alpha carbon, and that's going to be a secondary alpha carbon because carbon 2 is attached to two carbon chains, carbon 1 and carbon 3. The two different paths around the ring count as two different carbon chains, making carbon 2 secondary. Now we choose a mechanism. We have a secondary alpha carbon, which puts us in the middle row of the table. We're using O-, which puts us in the right-hand column of the table. So the table predicts an E2 mechanism. Make sure that you write that down. For an E2 mechanism, we know we're going to use the O- as a strong base. We know that we should look for alpha and beta carbons. Carbon 1 will be a beta carbon, and so will carbon 3. Two beta carbons attached to our alpha carbon, carbon 3 or carbon 1. So we've labeled our alpha and beta carbons. Notice that both of these beta carbons are attached to a hydrogen, so they both seem like candidates for E2. So let's go through these guidelines for applying E2 on a ring. So the first guideline is for E2, the beta hydrogen must be trans to the leaving group. So let's draw in those beta hydrogens on the ring. Carbon 7 was on a wedge. That tells me that this hydrogen must be on a dash. Remember, this is a tetrahedral carbon, so it should have two solid lines, a wedge, and a dash. Carbon 8 was on a dash. That tells us this hydrogen is on the wedge. As usual, we're drawing the wedge and the dash close to each other, adjacent to each other in the picture. Well, remember that the beta hydrogen must be trans to the leaving group. This hydrogen is trans to this leaving group. The leaving group is in front of the ring, and the hydrogen is behind the ring. So here we have the correct trans relationship. On the other hand, this beta hydrogen is cis to the leaving group. The hydrogen is in front of the ring, just like the leaving group. That means that this hydrogen cannot engage in the E2 reaction. This hydrogen cannot engage in the E2 reaction because there's no way that it could be anti to the leaving group. Remember that we need an anti-periplanar conformation between the leaving group and the hydrogen. Well, if the leaving group and the hydrogen are both on the same side of the ring, there's no way they could be pointing in opposite directions. This hydrogen is not actually a possibility for the E2 reaction because it's cis to our leaving group. So I'm going to go ahead now and erase this beta label. I'm going to erase this beta label because it turns out we're not going to use this beta hydrogen in the reaction. We're going to use this beta hydrogen it's allowable because it is trans to the leaving group. Because this hydrogen is trans to the leaving group, it's possible to fold this molecule so that the hydrogen is pointing anti to the leaving group. The first time I recorded this explanation, I left out a detail. Once we decide we're going to use carbon 1 as the beta carbon, we should also label that we're going to use carbon 1 as our weakly acidic carbon that's going to react with our strong base. Carbon 1 is going to act like an acid because it's going to give up a proton to the base. You will make fewer mistakes and you will develop your OChem skills more quickly if you make an effort to always label the specific roles that specific atoms play in your mechanisms. So we've used this rule. We're using the beta hydrogen that is trans to the leaving group. And notice that in this problem, this rule is not necessary. This is a rule that we would use to choose between the major and minor E2 product. But in this case, there's only going to be one E2 product. We don't have to choose between the two beta carbons here because we've already eliminated one beta carbon using this rule. So this rule is not relevant for this problem. This rule is only relevant if there are two beta carbons that have a hydrogen that's trans to the leaving group. Since in this case there was only one beta carbon with a hydrogen that was trans to the leaving group, this rule is not relevant. Now we can draw the E2 mechanism. Here's the arrow to show the base taking the beta hydrogen. Here's the arrow to show the pi bond forming between alpha and beta carbons. Here's the arrow to show the leaving group leaving the alpha carbon. Notice that for a ring, there's no need to use a Newman projection. For a ring, there's no need to use a Newman projection. Now we can draw the product. This arrow tells us to form a bond between the oxygen and the hydrogen. We change the charge on this oxygen from negative to neutral. This arrow tells us to break the bond between carbon 1 and the hydrogen and form a pi bond between carbon 1 and carbon 2. Here's that pi bond between carbon 1 and carbon 2. This arrow tells us to break the bond between carbon 2 and the chlorine. The chlorine started neutral and gained electrons, so it becomes negative. Now, this picture is not correct yet. This picture is not correct yet. Remember that in this picture, carbon 1 has changed from tetrahedral to trigonal planar. Therefore, we need to change this bond from a wedge to a solid line. I changed this bond from a wedge to a solid line. On the other hand, there's no reason to change the geometry around carbon 3. Carbon 3 didn't participate in the reaction, so I retained the dash over here. There isn't any need to keep drawing the beta hydrogen on carbon 3 since it didn't participate in the reaction, so I left it out of this product. Here's the product that the professor would probably care about in your answer. Now we're done. Now, this problem asked us for the major product, but you should understand that this is actually the only E2 product in this reaction. This is the only E2 product. We cannot use this beta carbon at all for E2 because the hydrogen is cis to the leaving group. So this is not actually the major E2 product. This is the only E2 product in this case. Notice again that there's no need to draw a Newman projection when you carry out E2 on a ring. Instead, you just have to check that your beta hydrogen is trans to your leaving group. Here's a more technical note. Remember that E2 requires the beta hydrogen and the leaving group to be anti-periplanar to each other. That's why they have to be trans to each other on the ring. Now, I should mention that this picture of the molecule doesn't show the hydrogen anti to the chlorine yet. They are on opposite sides of the ring, but they're not pointing in 180-degree different directions. To actually get the hydrogen and the chlorine to be anti, you would have to fold the ring into a chair cyclohexane picture. We would have to fold this ring into a chair cyclohexane picture in order to get the hydrogen to actually be pointing anti to the chlorine. but there isn't actually any need to actually do that for most problems. It isn't necessary to actually draw the chair picture where the hydrogen is actually anti to the chlorine. It's good enough to draw. It's good enough to know that you could draw that picture. Because we could draw that picture, we know that we can use this hydrogen for the E2. It's not necessary to actually draw the chair picture in this case to show the hydrogen anti to the chlorine. So for most problems that involve rings, it's sufficient just to choose the beta hydrogen that's trans to the leaving group. In the next video in this series, we will see some more complicated E2 reactions where it actually is necessary to draw the chair conformation of the ring. Now, do you see how we used this idea on this problem? There's no free rotation around these single bonds. We said on this problem that we could not use this hydrogen in the E2 because it's cis to the chlorine. Now, why didn't we just rotate the hydrogen so that it was trans? Why didn't we just rotate this hydrogen so that it's trans? Well, that's impossible because the hydrogen is part of a ring. In order to rotate the hydrogen, we'd have to rotate around this 2,3 single bond, but there is no free rotation around that single bond. So we cannot rotate this hydrogen so that it's trans to the leaving group because the leaving group and the hydrogen are both attached to the ring, which imposes rigidity. Please pause the video and try this problem. Now let's discuss. We can start by numbering the carbons. I'm not likely to make any mistakes with these carbons, so I won't bother numbering those. We can identify that the O- is likely to be a nucleophile or a base. Neutral bromine will be our leaving group, which makes carbon 3 the alpha carbon, and that's a secondary alpha carbon because carbon 3 is attached to two carbon chains, a carbon chain that starts with carbon 2 and a carbon chain that starts with carbon 4. Secondary alpha carbon puts us in the middle row of the table. O- puts us in the right-hand column of the table. The table predicts an E2 mechanism. Make sure that you write down the name of your mechanism. Now that we know that this will be E2, we know that we're going to use the O- as our strong base. And we know we need to look for alpha and beta carbons. So we could use carbon 2 as our beta carbon, or we could use carbon 4, because both carbon 2 and carbon 4 are attached to the alpha carbon, carbon 3. Now, both carbon 2 and carbon 4 have at least one hydrogen, so they're each candidates to be used in the E2 reaction. So we'll apply this guideline for a ring. For an E2 on a ring, the beta hydrogen must be trans to the leaving group. Let's draw in the hidden hydrogen on carbon 2. Carbon 7 is on a dash, so the hidden hydrogen must be on a wedge. Well, notice that this hydrogen is cis to the leaving group. They're both in front of the ring. That means that we can't use this hydrogen for the E2 reaction. For E2 on a ring, the beta hydrogen must be trans to the leaving group. So this is not a candidate because there's no way that this hydrogen could be anti to this leaving group. So I can go ahead and erase this beta. I can erase that beta because I'm not actually going to use that carbon as the beta carbon. Now, if we look at carbon 4 is in a sense attached to two hydrogens. It's attached to an ordinary hydrogen, but remember that deuterium is an isotope of hydrogen, which means it's a variant or type of hydrogen. Either the ordinary hydrogen or the deuterium could be used as the beta hydrogen. So which are we going to use as our beta hydrogen, the ordinary hydrogen or the deuterium? Well, we have to use the one that's trans to the leaving group. And that, in this case, would be the ordinary hydrogen. In this case, the ordinary hydrogen is trans to our leaving group. I can also go ahead and say that carbon 4 is going to be acting as a weak acid in this case, because that's the one that's going to give up its hydrogen. All right, I think we're ready now to draw our mechanism. Here's the arrow that shows the base taking the beta hydrogen, the arrow that shows a pi bond forming between alpha and beta carbons, and the arrow that shows the leaving group leaving. By the way, notice that we're not applying this guideline at all for this problem. We don't need this guideline. This is a guideline we can use when there's more than one beta carbon that we could use. But remember, in this case, there was only one beta carbon we could use. We could not use this beta carbon because the hydrogen was cis to the leaving group, not trans. So there was no need to apply this guideline. This isn't just the major product, this is the only E2 product. This is not just the major product, it's the only E2 product in this case because we used the only beta hydrogen that was trans to the leaving group. For this problem, we only needed this guideline. It wasn't necessary to apply this guideline. Let's see. Notice that we have to change the deuterium from a wedge to a solid line to accurately show the trigonal planar geometry in the product around carbon 4. The deuterium can no longer be on a wedge. It has to be on a solid line. On the other hand, carbon 2 stays on a dash because carbon 7 on carbon 2 stays on a dash because this is still a tetrahedral carbon. The main purpose of this problem was to give us more practice with following this guideline. For E2 on a ring, you can only use a beta hydrogen that's trans to the leaving group. We couldn't use this hydrogen for the E2 because it was cis to the leaving group. We could not use the deuterium for the E2 reaction because the deuterium, even though the deuterium is a variant of hydrogen, it was cis to the leaving group. Instead, we had to use the ordinary hydrogen attached to carbon 4 for the E2 because that was the hydrogen that was trans to the leaving group. Only a beta hydrogen that's trans to the leaving group could be in a anti-periplanar conformation, could be anti to the leaving group. Please pause the video and try this problem. Now we'll discuss. The ionic bond with formal charges is already drawn for us, so we know that O- will play the role of nucleophile or base. We notice here this starting material is an alkyl sulfonate, and we expect that this neutral oxygen will be our leaving group atom. I guess I should number the carbons. Remember that in an alkyl sulfonate, the alpha carbon is the carbon attached to the oxygen, carbon 2 in this case, not the carbon attached to the sulfur, not this carbon. We have a secondary alpha carbon. That puts us in the middle row of the table and the right column, so the table predicts an E2 mechanism. Let's write that down. So now we know that the O- will play the role of our strong base in the E2 mechanism. Label the beta carbons. The beta carbons here are carbon 1 and carbon 3. Those are the two carbons that are attached to our alpha carbon. Each of those has at least one hydrogen. So we need to check whether those, we're doing a ring problem, we need to check whether the beta hydrogens are trans to the leaving group. Well, this hydrogen that was drawn in for us is trans to the leaving group. This hydrogen is on a dash behind the ring, and the leaving group is on a wedge in front of the ring. So it is possible to use this hydrogen as the beta hydrogen in an E2. On the other hand, obviously, carbon 3 has two hidden hydrogens that we could draw in. Of course, I draw one on a wedge and one in a dash to show that carbon 3 is tetrahedral. Well, this hydrogen on a dash is trans to the leaving group. So this hydrogen and this hydrogen are both good candidates to use as beta hydrogens for the E2. They're both trans to the leaving group. So I'm going to continue to label both carbon 1 and carbon 3 as beta carbons because they can both be used in this reaction. Now, which will give us the major product? Well, now we can go ahead and use this rule, or at least this box. Now, normally the major product for E2 would use the more substituted beta carbon. But remember, there's an important exception, which occurs when you use tert butyl oxide. Well, I hope you recognized that this base is tert butyl oxide. This is the condensed notation for tert butyl oxide. Remember, the tert here stands for tertiary. This carbon is tertiary, attached to 3 methyl groups. And it's called butyl because there's 4 carbons total. So this is tert butyl oxide. So we're going to use our exception. and the major product will use the less substituted beta carbon. So I guess that would be this one. Oh, I guess we should label these here. So beta carbon 3 is secondary. Beta carbon 3 is secondary, attached to two carbon chains, carbon 4 and carbon 2. Whereas beta carbon 1 is tertiary. Beta carbon 1 is tertiary, attached to three carbon chains, carbon 6, carbon 2, and carbon 7 outside of the ring. So our major product here will use the less substituted beta carbon. Our major product will use the less substituted beta carbon with tert-butyl oxide. So our major product is going to use carbon 3. So I'll start by focusing on the mechanism for carbon 3, which will give us the major product. The first time I recorded this explanation, I left out a detail at this point. Since for the time being we're focusing on using carbon 3 as the beta carbon, I should have labeled that at this point we're going to be using carbon 3 as our weak acid. At this point we're going to draw the mechanism that occurs when carbon 3 gives up a proton to the base. Here's the mechanism. Notice that I'm using the hydrogen on the dash, not the hydrogen on the wedge. I need the hydrogen that's trans to the leaving group for this E2 mechanism. Here is that major E2 product. We've also shown that the leaving group is left and the base has taken the beta hydrogen. Remember, we're using tert-butyl oxide, for which the major product uses the less substituted beta carbon with a hydrogen that's trans to the leaving group. We prefer the less substituted beta carbon here because it has less steric hindrance. Tert-butyl oxide is a bulky base that already creates a lot of steric hindrance on its own, so it's easier for it to attack the beta carbon that has less steric hindrance. Notice that this molecule is simply the solvent in this reaction. This is a solvent that's not participating in the reaction. Obviously, this O- is much more reactive than this neutral oxygen. Now, this problem told us to draw both the major product and the minor product. We know there's also going to be another product, the minor product, from using the other beta carbon, from using this more substituted beta carbon. With tert-butyl oxide, the minor product will use the more substituted beta carbon that has a trans hydrogen. This carbon 1 also has a hydrogen that's trans to the leaving group, so this carbon 1 can also be used in the E2 mechanism. Here are the electron pushing arrows for that mechanism. The base takes the beta hydrogen, pi bond forms, leaving group leaves. Here's the products from that step. This is the minor product. Here's another detail I left out the first time I recorded this explanation. Since in this mechanism we're now focusing on carbon 1 as the beta carbon, I should have now erased this beta label and moved the beta label over to carbon 1 for this mechanism. And since we're now using carbon 1 as the beta carbon for this mechanism, I should have labeled that carbon 1 will now be acting as the weak acid for this mechanism, giving up its proton to the base. In this version of the mechanism, we used carbon 3 as the beta carbon, so carbon 3 acted as the weak acid, and I should have labeled that in this version of the mechanism, we're using carbon 1 as the beta carbon, so here we're using carbon 1 as our weak acid. Here are our answers. Notice that it was really crucial in this problem to notice that we were using tert-butyl oxide. I hope you've got into the habit of always noticing when tert-butyl oxide appears in the starting materials. Because we were using tert-butyl oxide, the major product used the less substituted beta carbon, carbon 3, which was secondary, and the minor product used the more substituted beta carbon, carbon 1, which was tertiary. Both of those beta carbons, both of those beta hydrogens were allowable to be used. Both of those beta carbons could be used for E2 because they both had a hydrogen that was trans to the leaving group. That's a requirement for E2 on a ring. We used two ideas here. We made sure that we only used beta hydrogens that were trans to the leaving group. This beta hydrogen is trans to the leaving group, and this beta hydrogen is trans to the leaving group. And because we were drawing both the major and the minor product, we used this rule for tert butyl oxide, using the less substituted beta carbon as the major product with tert butyl oxide, and the more substituted beta carbon as the minor product, since both the more and less substituted beta carbons had a hydrogen that was trans to the leaving group. So one big lesson here is keep your eye out for tert butyl oxide. Oftentimes tert butyl oxide changes the outcome of the reaction. We also got some more practice with a sulfonate leaving group. Please pause the video and try this problem. Now let's discuss. We can start by numbering. We can identify the O- as a nucleophile or a base. This looks like a sulfonate. So this is an alkyl sulfonate. This oxygen will be the leaving group atom. Carbon 2 will be the alpha carbon. Remember that in an alkyl sulfonate, the alpha carbon is the carbon attached to the oxygen. The carbon attached to the oxygen, not the carbon attached to the sulfur. It might not be 100% obvious from this condensed notation, but in this condensed notation, this sulfur is connected to this oxygen, to these two oxygens, and this sulfur is also connected to this carbon. This sulfur is bonded to this carbon, even though they're not right next to each other in the condensed notation. So this carbon is not the alpha carbon, and this is the alpha carbon. From the previous problem, you can see a more expanded notation for the alkyl sulfonate. So you can see in the sulfonate's attached to 3 oxygens and this carbon. That might help you to understand this condensed notation, which shows, again, the same sulfonate where the sulfur is attached to 3 oxygens and this carbon. This carbon's not the alpha carbon because it's not attached to a oxygen. It's attached to the sulfur. This is the alpha carbon. This is a secondary alpha carbon. So again, we're using the middle row and the right-hand column of the table, and we write down that we have an E2 mechanism. Let's make sure we have our beta carbons labeled. Carbon 3 is a beta carbon, and carbon 1 is our other beta carbon. So which of those beta carbons are we going to use to draw the product of this E2 reaction? Well, make sure that the beta carbon is actually attached to a hydrogen. Clearly, carbon 3 is attached to 2 hidden hydrogens. But did you realize that carbon 1 is not attached to any hydrogens? There are no hydrogens attached to carbon 1, because remember, a neutral carbon should have 4 bonds, and we can already see all 4 bonds. There's a bond to carbon 5, a bond to carbon 2, a bond to carbon 6, and then another bond to this carbon over here. So there's no room for any hydrogens on carbon 1. So I hope that you didn't do this. I hope you didn't do this and draw in a hydrogen. Do you see how this would be a mistake? It would be a mistake to draw in a hydrogen on carbon 1. There's no room for this hydrogen on carbon 1 because now there would be 5 bonds around carbon 1. 1, 2, 3, 4, 5. So that would be a mistake. So one thing we have to realize on this question is there are no hydrogens attached to carbon 1 because hydrogen 1 is already showing 4 bonds to carbons. So carbon 1 is a beta carbon, but it doesn't have any beta hydrogens. Since carbon 1 has no beta hydrogens, it can't participate in the E2 reaction. So I can go ahead and erase this beta label. I can erase this beta label. We know we're not going to use carbon 1 in the E2 reaction because it's not attached to any hydrogens. So here we're using this idea. Only a beta carbon that's attached to 1 or more hydrogens can be used for E2. Carbon 1 is not attached to any hydrogens, so it can't be used for E2. So we're going to use carbon 3 for E2. Of course, for a ring, you have to use a hydrogen that's trans to the leaving group. That's easy for carbon 3 because it's attached to 2 hidden hydrogens. There are 2 hidden hydrogens attached to carbon 3, and the one on the dash is trans to our leaving group. So that satisfies this guideline. We don't need to worry about this guideline. This guideline is only necessary when there's more than 1 beta carbon that we can use. There's only one beta carbon that we can use in this case, so this guideline is unnecessary. We can go ahead and draw our mechanism. I guess I can make a note that we're going to use carbon 3 as our weak acid. Here is our electron pushing mechanism. So here's the product from that E2 mechanism. We can avoid clutter by leaving out this hydrogen in the product, treating it like a hidden hydrogen. So the main issue that this problem was testing is, I think this problem is trying to tempt you into drawing in an extra hydrogen on carbon 1 and using a hydrogen on carbon 1 in the E2. The problem, I think, is trying to tempt you into putting the double bond over here. And we should see that that doesn't make sense. Remember, only a beta carbon that's attached to one or more hydrogens can be used for E2. And if you count the number of bonds that are already showing, you can see there's no room for any hydrogens at carbon 1. Remember that a neutral carbon should have 4 bonds total. A neutral carbon should have 4 bonds total. We knew there were 2 hidden hydrogens on carbon 3 because there were 2 bonds that were already showing. We know there's 0 hidden hydrogens on carbon 1 because there are 4 bonds that are already showing around carbon 1. Please pause the video and try this problem. Now we can discuss. We can start by numbering the carbons. The ionic bond and formal charges have already been shown for us. We can see that the O- will be a nucleophile or a base. The neutral chlorine will be our leaving group. The alpha carbon will be carbon 1. That's a tertiary alpha carbon. Carbon 1 is attached to 3 carbon chains, carbon 6, carbon 2, and carbon 7. The tertiary alpha carbon puts us in the bottom row of the table. O- puts us in the right-hand column of the table. So the table predicts an E2 mechanism. With an E2 mechanism, we'll use the O- as a strong base. For E2, we should label the beta carbons. The beta carbons are carbon 6, and carbon 2, and carbon 7. Carbon 7 is also a beta carbon because carbon 7 is attached to carbon 1, which is our alpha carbon. Now, all of those beta carbons have at least 1 hydrogen. They all have at least 1 hydrogen. So how do we know which one will give us the major product? Well, we know that for the carbons on the ring, we would have to use a hydrogen that's trans to the leaving group. Both carbon 6 and carbon 2 have hydrogens that are trans to the leaving group. The leaving group is on a wedge, and both carbon 6 and carbon 2 have hidden hydrogens that are on a dash. So both carbon 6 and carbon 2 could participate in an E2 reaction. Now, carbon 7 is outside of the ring. Carbon 7 is outside of the ring, so there's no such thing as the hydrogens on carbon 7 being cis or trans to carbon 1. Any of these hydrogens on carbon 7 could participate in an E2. There's free rotation around this single bond outside of the ring, so any of the hidden hydrogens on carbon 7 could easily rotate to be anti-periplanar to the leaving group. So how do we figure out the major product? Well, we have to use this rule, but we have to realize that we're going to use the exception because we have tert-butyl oxide. I hope you recognized that this is tert-butyl oxide, the bulky base. Carbon 9 is our tertiary, as a tertiary carbon in tert-butyl oxide. With tert-butyl oxide, the major product uses the less substituted beta carbon. Well, carbon 7 here is primary, whereas carbon 6 is secondary. Now, notice that this beta carbon is secondary. This beta carbon is secondary, but carbon 7 is primary. It's only attached to one other carbon. Now, since we're using this base tert-butyl oxide, we're going to use this exception. When using tert-butyl oxide, the major product comes from the less substituted beta carbon. Well, the least substituted beta carbon here is carbon 7, the primary beta carbon. So our major product will come from using carbon 7, not from carbon 6 or carbon 2, because carbon 7 is the least substituted. That's the main issue on this problem. The main trap students will fall into, I think, is a lot of students will use a beta carbon in the ring instead of using carbon 7. So remember, we need to notice that we're using tert butyl oxide. And with tert butyl oxide, the major product uses the less substituted beta carbon. In this case, that would be carbon 7, the carbon that's outside of the ring. So I'm going to erase these hidden hydrogens on carbon 6, and I'm going to erase this beta label on carbon 6 because we've decided that's not going to give us the major product. And I'll erase these hidden hydrogens on carbon 2 and erase the beta label for carbon 2 because we've decided that this carbon is not going to participate in the reaction. Instead, we're going to be using carbon 7 as our beta carbon. The least substituted beta carbon is used when we're using tert butyl oxide. That's this rule. And this rule. The first time I recorded this explanation, I forgot to take care of a detail at this point. Since we've decided that we're going to be using carbon 7 as our E2 beta carbon, at this point I should have made a note that we will be using carbon 7 as our weak acid. Carbon 7 is the acid that's going to give up a proton to the base in the major E2 product. Anytime you've recorded which atom you're going to be using as your base, it's best for completeness to also record which atom you're going to use as your acidic atom. Remember, we don't have to worry about the hydrogens here being cis or trans to the leaving group because these hydrogens are outside of the ring. There's free rotation on this single bond outside of the ring, so any of the hydrogens on carbon 7 could rotate to be anti-periplanar to this leaving group. Well, now we can draw our mechanism. Notice that we have to draw in an extra bond to show one of the hidden hydrogens on carbon 7. Now, I'm not going to bother to try to draw this hydrogen as being anti-periplanar to the chlorine. That's not an issue here. I guess we should be using the straight chain approach now. Because carbon 7 is outside of the ring, we should be using the straight chain approach. We don't need a Newman projection, or we don't really need to worry about stereochemistry, because carbon 7 is not a stereocenter. Remember, we'd only need a Newman projection if both the alpha and beta carbons were stereocenters. Actually, in this case, I guess neither of them is a stereocenter. So carbon 7 is not a stereocenter, and neither is carbon 1. So we're not going to bother with a Newman projection. We don't need to try to worry about rotating the hydrogen to be anti-periplanar to the chlorine. The main reason to do that would be to get the correct stereochemistry for our product. And it turns out that the product won't have any interesting stereochemistry. Let's just go ahead and draw the product. Okay, here's that product. Notice that in this picture, carbon 7 is on a dash, but we changed that to be 2 solid lines here because carbon 7 and carbon 1 are now trigonal planar in this product. So I think maybe most students would get this wrong because most students would draw the double bond inside the ring. I think most students would use carbon 6 or carbon 2 as the beta carbon. They might not, a lot of students wouldn't even realize that carbon 7 was a candidate for being the beta carbon here. Maybe because it's outside of the ring or maybe because it's on a dash. So remember to start by carefully labeling all of the possible beta carbons until you decide which beta carbon you're actually going to use. Also, keep your eye out for tert butyl oxide. Tert butyl oxide can change the result of a reaction. With tert butyl oxide, we want to use the less substituted beta carbon for the major product. And this problem was asking us for the major product. Did you get this problem right? This problem is a good test of whether you're taking care to watch out for tert butyl oxide and whether you understand that with tert butyl oxide, the major product comes from the less substituted beta carbon. Please pause the video and try this problem. Now let's discuss. Let's start by numbering all the carbons. There are no ionic bonds. Notice that oxygen and hydrogen are both non-metals. So this OH bond is covalent. So there are no formal charges that we have to draw in anywhere. So we can start trying to assign some roles. Now, normally we would start by looking for formal charges to help us assign the roles, but again, there are no formal charges here. We do see this neutral oxygen, which has a lone pair. Well, an oxygen with a lone pair neutral can be a nucleophile or a base. The best clue for a nucleophile or a base is a negative formal charge. But another clue is a neutral atom with a lone pair, such as an oxygen. A neutral atom with a lone pair, such as an oxygen, could be a nucleophile or a base. The lone pair makes the atom willing to donate electrons. Remember that a nucleophile and a base are both electron donors. The neutral chlorine can be a leaving group. That makes carbon 1 our alpha carbon, and we can see that that is a secondary alpha carbon. So now we can use our table to choose a mechanism. Secondary alpha carbon puts us in the middle row of the table, and we have a neutral oxygen as our nucleophile or base. It's the neutral oxygen in an alcohol. And that means that the major product will be SN1. So we should write that down. We expect an SN1 mechanism. The main purpose of this video series is to discuss E2 mechanisms, but when you take your real exam, all the mechanisms will be mixed up. So it's important to be on your guard and not assume that the mechanisms are E2. I hope you didn't assume that this would be an E2 mechanism. I hope you realized this would be SN1. By the way, is this molecule tert-butyl oxide? I hope you saw that this molecule is not tert-butyl oxide, even though it looks somewhat similar. This molecule is tert-butyl oxide. I hope you can see the difference between them. The most important difference is that this oxygen has a negative formal charge, and this oxygen has 0 formal charge. Remember, the most important factor in organic chemistry is the formal charge. Different formal charges mean different compounds. So this is not tert-butyl oxide because it doesn't have a negative oxygen. Instead, this would be called tert-butyl alcohol. Can you see why that's a reasonable name? We do have a tert-butyl group. This is a tert-butyl group. Carbon 8 here is tertiary, and we can still use the term butyl here because there are 4 carbons total. But notice that this is an alcohol. You should know that an alcohol is an OH group connected to a carbon chain. So this is tert-butyl alcohol, which is a similar but quite different compound from tert-butyl oxide. Notice that the "ide" in oxide refers to the negative oxygen. When the starting materials include tert-butyl alcohol, we're using the left-hand column of the table with a neutral oxygen. When the starting materials include tert-butyl oxide, we're using the right-hand column of the table, where the starting materials include a negative oxygen. So this shows you how important formal charges are. There's a huge difference between an oxygen with a negative formal charge in the right-hand column of the table and an oxygen with no formal charge in water or alcohol in the left-hand column of the table. By the way, sometimes I see students get confused. Sometimes students on this problem get confused and say that carbon 8 is the alpha carbon. Is carbon 8 the alpha carbon? If carbon 8 was the alpha carbon, we would have a tertiary alpha carbon. So should we say that we have a tertiary alpha carbon because of carbon 8 or a secondary because of carbon 1? Well, remember that in this context, in this table, the alpha carbon in the table refers to the carbon attached to the leaving group. Carbon 1 is the carbon attached to the leaving group. This oxygen, this neutral oxygen, is not an acceptable leaving group. So carbon 8 is not treated as the alpha carbon. In this table, the term alpha carbon refers to the carbon attached to the leaving group. So carbon 1 is the alpha carbon in this problem. Carbon 8 is not referred to, it's not useful for us to refer to carbon 8 as the alpha carbon. Therefore, we do say that the alpha carbon is secondary on this problem, not tertiary. So this problem gives us a chance to refresh our memory of what happens in an SN1 mechanism. Do you remember? How many steps are there in an SN1 mechanism, and what happens in those steps? You should know that there are 2 main steps in an SN1 reaction, and sometimes we also need an acid-base step. I went over SN1 reactions in much more detail in the SN1 series. Here we'll briefly review how to write an SN1. Let's see. Now, notice that One thing we can say here is that an SN1 involves a nucleophile, not a base. So I'll adjust this to show that we expect the neutral oxygen to be a nucleophile, not a base. In our first main step, the leaving group leaves the alpha carbon. So I'll draw that electron pushing arrow to show this leaving group leaving the alpha carbon. That's all that happens in the first step of an SN1 reaction. So now we can draw the product of that step. This electron pushing arrow tells us to erase the bond between carbon 1 and the chlorine. Make sure, most importantly, that you change two charges. Carbon 1 started neutral, and carbon 1 is losing electrons from this electron pushing arrow. So carbon 1 ends up with a positive formal charge. The chlorine started neutral and is gaining electrons, so the chlorine ends up with a negative formal charge. The most common mistake on this step would be forgetting to change the formal charge for carbon 1, which is losing electrons at the beginning of the arrow. Always make the atom that loses electrons from the arrow one step less negative. That means one step more positive. Now this doesn't look like an acceptable final product because the main product here still has a formal charge. So let's go on to our second SN1 step where the nucleophile joins the alpha carbon. So now we'll use the oxygen as our nucleophile. So I guess I should make a note here that step 1 was what we could call a leaving group step. Step 2 will be a nucleophile electrophile step, and we will be using carbon 1 as our electrophile. We can see that carbon 1 is a good electrophile because of its positive formal charge. In the SN1 series, we discussed that a positive formal charge on a carbon makes the carbon want to act as an electrophile. The positive formal charge makes the carbon want to receive electrons. So we should draw the electron pushing arrow to show the nucleophile joining the alpha carbon. Notice that, of course, for SN1, there's no need to label the beta carbon. For SN1, we only care about the alpha carbon, not the beta carbon. Here's our electron pushing arrow. Now we can draw the product from that step. This arrow tells us to form a bond between this oxygen and carbon 1. I've drawn the bond between the oxygen and carbon 1. Most important is the formal charges. This oxygen started neutral and lost electrons, so it should become one step less negative, one step more positive. This oxygen ends up with a positive formal charge. Carbon 1 started positive and gained electrons, so carbon 1 changes to neutral. The most common mistake on this step would be forgetting to change the formal charge on this oxygen. Since the oxygen is losing electrons at the beginning of the arrow, the oxygen should become one step less negative, one step more positive. Now we've completed these two main steps for SN1, but it doesn't seem like we're done because our main product still has a formal charge. When your main product has a formal charge, that's usually a clue that you're not done with the mechanism yet. Are we going to get rid of this positive formal charge? With an acid-base cleanup step. We can use an acid-base step to clean up this positive formal charge. Identify who will play the role of the acid and who will play the role of the base. While this positive formal charge tells you that the oxygen will play the role of a strong acid. In the SN1 series, we saw that an atom with a positive formal charge can play the role of a strong acid. The positive formal charge makes it want to receive electrons, which is what an acid does. Who's going to play the role of the base? Well, we should use another molecule of this alcohol as the base. We already used this alcohol in the first step as a nucleophile, but the alcohol here is the solvent, and the solvent is always going to be present in great excess, so there should be plenty of alcohol left over to allow us to use the alcohol again as a weak base. There's also Cl- But it turns out that Cl- is a very weak base, so we prefer to use the alcohol as the base. Again, in the SN1 series, we saw that Cl- is a very weak base, and therefore when alcohol or water is used as the solvent, we prefer to use the water or alcohol as the base rather than a Cl-. The clue that water or alcohol can act like a weak base is that they have neutral oxygens with lone pairs. Let's draw the electron pushing arrows. I hope you know how to draw the electron pushing arrows for an acid-base step. Remember that a base donates electrons to take a proton. So we put the base at the beginning of the electron pushing arrow to show that it's donating electrons. And we put this proton, this hydrogen, at the end of the electron pushing arrow. Make sure that you understand how to draw the electron pushing arrows for this acid-base step. That gives many students difficulty. Now we can draw the products from that step. This arrow tells us to form a bond between this oxygen and this hydrogen. So we show that now the oxygen is bound to 2 hydrogens instead of to 1 hydrogen. Most important, change the formal charge. This oxygen started neutral and lost electrons, so this oxygen ends up with a positive formal charge. Now we have this electron pushing arrow, which tells us to break the bond between the hydrogen and the oxygen, which we've already done. The oxygen started positive and gained electrons, so the oxygen ends up neutral. Again, the most common mistake here would be forgetting to change the charge on this oxygen at the beginning of the series of arrows. So here's our product. Now the main product has no formal charge. It wasn't possible for us to get rid of this formal charge or this formal charge, but our main product, so to speak, has no formal charge, and that's a clue that we're done with this mechanism. So I circled the product that the professor would probably care about for this problem. So we reviewed here that SN1 reactions have 2 main steps, but that SN1 reactions also often involve an acid-base step. We saw here how we needed an acid-base cleanup step after the 2 main steps to get rid of the positive formal charge on the main molecule. This problem should have been boringly easy for you. If this problem was not boringly easy, you might want to watch or rewatch my earlier series on SN1 mechanisms. And the main purpose of this problem is to remind you that you can't assume that any reaction is E2. You have to use the table to figure out what the correct mechanism is. And again, remember, don't assume that this molecule is tert butyl oxide. It's not. It has a neutral oxygen, so it's just a regular alcohol, tert butyl alcohol. By the way, I hope it's obvious to you that carbon 8 should stay connected to this oxygen in the product. How do we know that carbon 8 stays connected to this oxygen? Well, because carbon 8 is covalently bonded to this oxygen, and you should only break a covalent bond if an electron pushing arrow tells you to. There's no electron pushing arrow that tells us to break this bond. That's how we know that this oxygen stays covalently bonded to carbon 8 in the products. Please pause the video and try this problem. Now let's discuss it together. We can start by numbering the carbons. We should notice that we have a metal-non-metal bond here, which means this bond is ionic. So we should assign the formal charges, plus and minus. So we can start assigning roles. When we see O-, we expect that to be a nucleophile or a base. Neutral bromine looks like it can be a leaving group, which would make carbon 1 our alpha carbon. And that would be a secondary alpha carbon. Now let's use the table to determine the mechanism. A secondary alpha carbon would put us in the middle row of the table. O- would put us in the right-hand column of the table. So the table would predict an E2 mechanism. Make sure that you write that down. But wait, what about this neutral oxygen? What role will this neutral oxygen play? Could we perhaps use this neutral oxygen as our leaving group? And in that case, could we use carbon 9 as our alpha carbon? We know neutral bromine is a good leaving group. Is this neutral oxygen a good leaving group? Well, no, neutral atoms are usually not acceptable leaving groups. There are some specific exceptions that we've memorized, like neutral chlorine, bromine, and iodine, and neutral sulfonates, but otherwise we usually assume that neutral atoms are not acceptable leaving groups, unless there's a specific reason otherwise. So no, this neutral oxygen is not a good leaving group. This neutral oxygen is not a good leaving group. So no, we're not going to use carbon 9 as the alpha carbon for an E2 because it's not connected to a good leaving group. I suppose we should also consider carbon 10 as the alpha carbon. We could also consider using carbon 10 as the alpha carbon. It's also connected to this neutral oxygen. So no, we cannot use carbon 10 as the alpha carbon because it's not attached to a good leaving group. This neutral oxygen is not a good leaving group. So we go with our first instinct. We'll proceed with our first instinct and carry out an E2 mechanism on carbon 1. So that was the main issue here. So what role is this oxygen going to play? Well, it's really mainly here just to distract us. The oxygen's not going to play any significant role in the reaction. It's really here just to distract us. The key thing is to realize that it's not an acceptable leaving group, and therefore we cannot use either carbons 9 or 10 as the alpha carbon. So we've decided that we're going to carry out an E2 mechanism, which makes O- play the role of a base. We know O- is a strong base. Here are our E2 guidelines. We should label the beta carbons. Carbon 1 is our alpha carbon, so we could use carbon 2 as a beta carbon, or we could use carbon 9 as a beta carbon. But remember that for E2, the beta carbon must be attached to a hydrogen. Carbon 2 is attached to 2 hidden hydrogens, but did you notice there are no hidden hydrogens on carbon 9? Remember that a neutral carbon should have 4 bonds. Well, you can already see 4 bonds shown around carbon 9. Carbon 9 is shown as bonded to carbon 5, carbon 1, carbon 8, and also this oxygen. Since there are 4 bonds shown, there's no room for any hidden hydrogens on carbon 9. So carbon 9 is a beta carbon, but we can't use it for an E2 reaction because it's not attached to a hydrogen. Remember, don't assume that there's a hidden hydrogen. You have to check if there's a hidden hydrogen. So we've determined that we're going to use carbon 2 rather than carbon 9 as our beta carbon. We should follow the guidelines for E2 on a ring. Remember that the beta hydrogen must be trans to the leaving group. So we will use the hydrogen on the wedge rather than using the hydrogen on the dash. Well, this is another case where the first time I recorded the explanation, I labeled the base, but I forgot to label the acid. Once I had decided that we were going to use carbon 2 as the beta carbon for the E2 mechanism, I should have labeled that carbon 2 would play the role of weak acid in that mechanism, giving up its proton to the base. This rule is not relevant here. This is a rule that we would use for choosing between 2 possible beta carbons, but there's only 1 possible beta carbon that we could use here because this one had no beta hydrogens, so this rule is not relevant in this case. Now let's draw our mechanism. Here's our mechanism, and we can draw the product. This arrow tells us to form a bond between this oxygen and this hydrogen to form H2O. The oxygen started negative and lost electrons, so it becomes neutral. This arrow tells us to break the bond between carbon 2 and the hydrogen and form a pi bond between carbon 2 and carbon 1. This arrow tells us to break the bond between carbon 1 and the bromine. The bromine started neutral and gained electrons. The bromine ends up with a negative formal charge. If you were going to draw the remaining hydrogen on carbon 2, you would have to draw it on a solid line rather than on a dash, but the simplest thing is just to leave out the hidden hydrogen completely. So when you see this neutral oxygen here, you should say to yourself, this neutral oxygen is not a good leaving group, therefore we cannot use carbon 9 or carbon 10 as the alpha carbon. So this neutral oxygen is pretty much just a distraction that's not participating in the reaction. Also, remember that we decided not to use carbon 9 as our beta carbon because it wasn't attached to any hidden hydrogens. Only a beta carbon with a hydrogen can be used for E2. Please pause the video and try this problem. This review quiz problem. Well, here's the answer. You can find the answers in this handout. SN2 reactions have one main step, in which the nucleophile joins the alpha carbon and the leaving group leaves the alpha carbon. SN1 reactions have two main steps. In the first step, the leaving group leaves the alpha carbon. In the second main step, the nucleophile joins the alpha carbon. And as we saw, sometimes you also need an acid-base step for an SN1 mechanism. And as we've been practicing, E2 reactions occur in one step. One complicated step where simultaneously a base takes a beta hydrogen, a pi bond forms between alpha and beta carbons, and simultaneously the leaving group leaves the alpha carbon. When you take your exam, you're going to have to keep switching gears and moving back and forth between SN2, SN1, E2, and later E1 mechanisms. So it's crucial that you don't get them confused and crucial that you have this information in the table memorized. Make sure that you have this information in the table memorized so that you can switch gears and answer exam questions that involve a mixture of these different types of mechanisms. Did you find this video to be helpful? If so, you can support the videos by using the PayPal donate button on my website to make either a one-time donation or a monthly pledge. You can visit my website by clicking the link on the screen or by using the link in the video description box. Thank you.